Okay, so hello. So right now I will be studying the force deformation relationship in the ASCE 41 and the performance-based evaluation. Okay, so this module, disclaimer, this module is from Dr. Fawad Najam, and this discussion is only for personal use and should not be taken this recording as a supplemental discussion for the nonlinear modeling and analysis of RC building. So I did not take any uh, ownership on this PDF or this document. So the document is all published and written by Dr. Fawad Najam. Okay, so today I'm studying the force deformation relationship in the ASCE 41 and the performance-based evaluation. Okay, so yung seismic design guidelines for tall buildings such as the PR 2010 discusses the two levels of performance-based seismic assessment. Okay, so what are those? So according to the peer, meron silang service level evaluation or yung SLE and the maximum considered earthquake or the MCE level. Okay, so as I've known, yung SLE or the service level earthquake or service level evaluation have 50 years return period, and the MCE is 2470 or 475 years return period of earthquake. So ganun kalakas tong maximum considered earthquake, so ganun siya katagal yung return period. And this one is yung service level earthquake is 50 years return period lang. Okay. Meron pa dito isa the design-based earthquake. So we're asking the design-based earthquake is 2/3 of the MCE. So yun. So these two are generally involved comparison of the force and the deformation demands imposed by the specified earthquake hazard to corresponding limit state, capacity of the structural components and the systems. So for the performance based evaluation of components under the several performance such as the immediate occupancy, life safety, and the collapse preventions are defined and marked on the nonlinear force deformation relationship assigned to the plastic hinges. Okay? So ito yung mga material stress strain curves in the case of fiber modeling. So generally in the plastic hinge modeling, 5 points are labeled A, B, C, D, and E are used to define the force deformation behavior of the plastic hinges. Okay, so the points corresponding to various performance such as the immediate occupancy, IO, life safety, and the collapse prevention. Okay, these performance levels are specified as the acceptance criteria for the hinge in given in the figure 1-23. So this one. Okay. So kapag na-plot natin yung capacity curve, so yung capacity curve is 'di ba nag-define tayo ng displacement, so push like the pushover analysis. Okay, so nag-define tayo ng displacement. So pagka-push, unang makikita yung plastic hinge, then yun yung displacement. Kung anong displacement yun. So parang ganito siya. So pagka-push nung force, okay, nung force dito, okay, may lalabas na, let's say this one is the first plastic hinges. So ipa-plot 'yon sa capacity spectrum, this one. Okay, so I think the graph is this one. So medyo ganito yung graph. Okay. So this one is yung roof displacement. And this one is yung base shear. Okay. So yung this plot, ang tawag dito is capacity spectrum. So ibig sabihin, ito yung capacity ng frame natin, ng structural frame natin. So ipo-plot niya sa makikita yung roof displacement or yung anong roof displacement nagkaroon ng first plastic hinging. Then next is this member is collapse na. So tatanggalin na ng analysis yan, or let's say ETABS. Then mag-iteration again to solve for next plastic hinges and to create a collapse mechanism. So ipo-plot yan isa-isa. Okay, so yung equivalent base shear niya dito. So this one is yung capacity spectrum. Okay. So ano yung acceptance criteria or the demand force? Or sorry, what are the acceptance criteria? So for the acceptance criteria, ito yung this one. So the acceptance criteria based on the ASCE 41. So minark niya as IO, immediate occupancy, life safety, and collapse prevention. Okay. So kapag nandito sa IO is immediate occupancy is during earthquake, so pwedeng may occupants pa yung building. And this one, yung life safety is magkakandak na ng preliminary tawag dito ng safety measures. Okay? And this one, yung collapse prevention is medyo aalis na dun sa building and you need to reassess your building for occupancy. Okay. So describe what are the acceptance criteria. So the performance assessment using the nonlinear analysis requires a set of criteria defining the acceptable performance. So these criteria are the capacity of a particular member corresponding to a particular performance level. Therefore, the terms deformation capacity and acceptance criterion can be interchangeably used in the context of the nonlinear modeling and analysis. So yung demand capacity, the deformation capacity and the acceptance criterion is can be interchangeably used. Okay? So yung force deformation controlled actions, so this capacity are specified in terms of the deformation measures. So the plastic rotation for beam hinges or the material strains for the columns and the fibers. Okay, so this capacity should either be determined experimentally or from reliable guidelines developed based on the extensive experimentation. Okay, so one of such reliable and useful guideline in the ASCE 41 is this one. So it is a standard for the seismic rehabilitation such as retrofitting of an existing building. So however, it also be used for the design and performance evaluations of the new buildings. Okay, so performance evaluation, so for a new building, you can use this ASCE 41 guidelines. So it was published in 2006 by the SEI and ASCE. So following earlier publications and pre-standards, including the ATC 40 and the FEMA 273 and the FEMA 356 in 1996, 1997, and the year 2000 respectively. Okay, so beside the detailed structural evaluation and retrofit methodology and analysis procedures based on the ASCE 41, it also provides a modeling guidelines for inelastic analysis and performance assessment of different structural components. Okay, so for the plastic hinge modeling, it recommends deformation capacity for a wide range of components for the immediate occupancy, the life safety, and the collapse prevention. Okay, so the ASCE 41 also recommends modeling parameters which essentially define the shape of the force deformation relationship. It also allows the force deformation relationship of for a structural component to be obtained from the experimental data. So if this is not feasible, the relationship shown in the figure 1-24 can be used. Okay. In the FEMA 356 and the ASCE 41 force deformation relationship. Okay, so okay. So dito, sabi dito sa ASCE 41 plastic deformation from point B to point C, ito yung ASCE 41 plastic deformation. And this one, usual definition of plastic deformation, the FEMA 356 assumption for the strength loss. Okay, so yung point C to point D, ito yung strength loss. And from point B to point C, nandito yung plastic deformation. Okay, so plastic deformation. Then next is strength losses from C to D. Linear strength loss. Okay, so ito yung ano niya. Okay. Okay. So yung acceptance criteria for this one, so pwede natin gawin, i-plot natin yung displacement and the force deformation relationship or force displacement relationship of our actual frame. Then kakandak niya yung kakandak nila yung ano yung acceptance criteria. So I think meron ako dito. Okay, so this one is from the lecture of Dr. Ignacio in Earthquake Engineering. So Professor Ignacio is one of my professor in Earthquake Engineering in my MS in Structural Engineering in UP Diliman. So this lecture, according to him, based on this lecture, this one is yung capacity spectrum method of the ATC-40. Okay, so ang nangyari dito during the pushover analysis, so yun nga, plinat yung roof displacement versus the base shear. So yung roof displacement, pinaplat yung kung saan nakikita yung plastic hinges. Then ipaplat yon. Okay, kunwari, andito yung plastic hinge. Okay, at this displacement, ito yung plastic roof displacement. Then ito yung equivalent base shear, this one. Okay, yan. So plinat yon. Okay. Then after that, yung base shear will be converted to capacity spectrum. So yung pushover curve, this one, yung pushover curve is converted to a capacity spectrum. Okay, so paano kino-convert yon? Okay, so I remember the conversion is somewhat equivalent to force is equals to mass times area, or the acceleration, mass times acceleration. Okay, and this one, syempre, the base shear is equivalent to mass times the spectral acceleration. So therefore, we can solve for the spectral acceleration. So kung mapapansin natin dito, para lang siya nag-shift. Okay, nag-shift lang yung ating curve. Okay, so yun yung capacity. Ito yung capacity ng ating structure. Okay, so paano natin malalaman yung demand? Okay, di ba? The basic of structural engineering is to compare the demand and the capacity, di ba? And versus the capacity. Okay. So paano malalaman yung demand? Yung demand, tama. Paano malalaman yung demand? Okay, to determine yung demand, okay, for example, we have the response spectrum at effective damping. Let's say a building of a 5% damping, okay, fixed, constant yung damping, effective damping of 5%. And kung mapapansin dito, this one is a response spectrum. Okay, so whereas yung spectral acceleration versus yung sa time period. Okay, so this one is yung response spectrum of a building with CA and CV parameters. So I can see that this one is based on the UBC 1997. Okay. So to convert this response spectrum to spectral acceleration versus spectral displacement graph, so you need to convert the response spectrum to acceleration displacement response spectrum format or the demand spectrum format. Okay, so to convert that, ang gagawin lang naman doon is yung spectral displacement is equal to the spectral acceleration times the squared of the period of your building, or sorry, yung time period na naka-plot dito divided by the 4 pi squared. Okay? So this one. So pwede mo na siyang ma-convert yung response spectrum into acceleration displacement or the demand spectrum curve. So now we can compare na yung demand spectrum versus the capacity spectrum. Okay, this one. So if we compare the two, we can determine if our building is safe or not. Okay, so we can also determine the performance point. Okay, the performance point is the intersection of the demand spectrum and the capacity spectrum. Okay, so this one is yung demand spectrum for a given effective damping and location and the level of earthquake. And this one is yung capacity spectrum. Okay? So, ganyan yung ating to determine the performance point. Okay, so to determine then yung the verification of your of the acceptance, ang ginagawa nila, okay? So, yung deformation measure versus the force measure graph. Okay, this one, yung plot dito within this range is yung performance limit. Ito yung immediate occupancy, life safety, and the collapse prevention. Okay, so yan yung verification of acceptance. Okay, so basically the same lang sila halos. The same lang sila halos nung dito. Okay, hindi lang na-discuss dito how to solve for the demand spectrum. Okay, sige. Yung next naman is we have the question, which modeling approach should be used and for what application? Okay, so I think this one will be the last topic for the chapter 1. Okay, so the question is, which modeling approach should be used for and what application? Okay, so the choice of model type for a given application involves a balance between reliability, practicality, and computational efficiency. Okay, so subject to capabilities of available software and the computational resources. Okay, so the optimal model depends on many factors, including the structural system and materials, governing modes of the behavior, the expected amount of nonlinearity, and the level of detail available for the input and output data. Okay, so the reliability of the model comes from its ability to capture the critical types of deformation that are of interest to the modeler and control the response. Okay, so this one, syempre, we as a structural engineer, meron lang tayong three criteria, di ba? So yung three criteria natin is based on strength, based on serviceability, and based on economy. Okay, so we need to also consider yung economy ng design natin. So hindi porket mangyayari parang over design na yung structure natin. Okay, so ayan, we need to consider then, and also syempre yung computational efficiency. So under din siya sa economy. So kunwari nga meron kang structure, then sobrang tagal naman siya isolve ng computer, o sobrang complicated yung structure, so parang napagastos lang yung designer or yung client. Syempre yung client babayaran yung engineer na magde-design sa kanyang building. Okay? Next is this one. Sorry, this one pa. Siyempre, yung reliability rin ng model comes from the ability to capture the critical types of deformation that are interest of the modeler and control the response. So, the famous line we have here in the Philippines, di ba? We have the GIGO. Okay, the GIGO is garbage in, garbage out daw. Okay? So I think hindi naman yun, I think that's not right eh. So dapat ano dito eh. What you input is what you expect. Okay. So, ayun. Next naman is yung plastic hinge and spring models have the advantage of being computationally efficient by modeling highly nonlinear effects in localized region of the structure with a few degrees of freedom. Okay, so mas maganda daw yung plastic hinge modeling when compared to fiber modeling. Okay, yung models generally employ predefined functions to define the nonlinear response of the components. So concentrated spring models are typically implemented to capture a single degree of freedom, such as the moment versus rotation, but they may include multi-axial response through the yield surface. So we have yung PX, MX, and MY interaction. Okay, so by capturing complicated behavior with highly idealized models, concentrated hinge models are very versatile. So, but they are also empirical and limited to modeling phenomena over the range of components and behavior modes for which they have been calibrated. Okay, so for beams and columns naman, okay, yung fiber models provide the capability to numerically integrate material response through the member cross sections at a more fundamental material level. Okay, so the fiber integration through the cross section can be used either in conjunction with a finite length hinge zone or a model formulations with that simulate the distributed inelasticity along the member length. Okay, so fiber type models for beams and beam column generally invoke kinematic assumptions such as the Euler-Bernoulli principle. Diba sa Euler-Bernoulli principle, the plane section remain plane under stresses. Okay, so assumption to relate uniaxial stresses and strains through the member cross-section to stress resultants and generalized strains for the cross-section. So example, we have the moment versus the curvature or the axial force versus the axial strain. Okay, so to the extent of these assumptions reflect the underlying member response, so they offer a tremendous benefits. However, one should be mindful of the limitation posed by the kinematic assumptions. For example, the Euler-Bernoulli assumption precludes cross-section warping or distortion due to the shear and torsional effects, due to the local buckling or the steel reinforcing bars or the steel webs or in the flanges, and the slip between the components of the section, or the material cracking and crashing. Although certain of behavior can be incorporated in the fiber material response, such as the steel materials that are calibrated to simulate the reinforcing bar buckling, or concrete models with tension softening. Okay, so these adjustments require empirical calibration that negates some of the appeal of the fundamental aspect of the fiber type models. Okay, and lastly, the continuum finite element models. Okay, so for the continuum finite element models, it represents the behavior at the most fundamental level and provide the ability to model the complete interaction of a three-dimensional behavior, including the complex geometries and multi-axial stress and strain states. However, three-dimensional continuum models are the most computationally intensive, particularly where the numerical mesh refinement is controlled by the smallest dimension of the member. So the finite element meshing through the thickness or depth of a member will dictate the mesh size required along the member length. Okay. So for this reason, yung 3D continuum models are typically only used to simulate portion of an overall system. So in addition, while continuum models offer a potential for capturing response of very fundamental levels, their practical application is limited by both computational resources and data to calibrate certain localized behavioral effects. So for example, a 2D shell or a 3D continuum finite element models can capture the response of isotropic steel materials fairly well. Okay, whereas many unresolved challenges remain for simulating the detailed behavior of a reinforced concrete members. So considering concrete cracking, dilation, and interaction between steel reinforcing bars and the concrete or the band and the anchorage. Okay, so the modeling decisions are centered on how simplified versus a complex the structural model should be. And the needed level of complexity of the model depends also on the aspect such as the expected failure modes and their consequences and their consequences and the anticipated location of damage and the anticipated level of nonlinearity. Okay, so this one is need to kailangan natin itong i-consider. Okay, so yung modeling decision natin is centered on how simplified versus a complex yung kailangan natin sa model natin. And also, ano ba yung kailangan nating response na to solve for that failure modes or that problem. Okay. I think that's it for this discussion. Okay. So next study session, we will discuss the nonlinear modeling capabilities of the ETABS 2016.